the WCNPS and the last day of our workshop. And in this first part of the morning, we will have two talks from Professor Juan José Murilo Fuentes and Benjamin Fuchs. And we'll start with Professor Juan José Murilo Fuentes, who received the telecommunications engineering degree from the University of Seville in Spain in 1996, and the PhD degree from the University Carlos III of Madrid in 2001. And he has collaborated with many training courses from telecommunication companies like Vodafone and Motorola, and also he became an associate professor in 2005, and also a full professor in 2016 at the University of Seville. And his research interests include machine learning, array processing, algorithms for wireless communications, and currently his interests move towards learning issues with emphasis on handwritten recognition and crowdsourcing to estimate received power levels in wireless communication systems. So let's pass the word for Professor.
Thank you, Ricardo. First thing, I just would like to thank you for coming. And second, I would like to also thank the organization for inviting me, to Joao, and especially Bruno for the arrangements. And also I would like to point out that this is a joint work with two other people in my department and one more in Universidad Carlos III de Madrid. One of them is Irene, that is just defending her PhD in 2 weeks. And most of the results we are going to talk about today are results of her thesis. Okay. Our research groups in Seville are the one I include here. We are working on the planning for handwriting recognition. We are also investigating on image processing for some old canvases restoration. We are also working on Gaussian processes, and particularly we are working on complex valued algorithms with kernels. And in the last line I include here is the topic for the today talk. So let's move to it. It's really hard to explain all these things, but let me put it in a way from an easy understanding to a more complex details. So what we are doing first is just to introduce the problem in this motivation section. Then we will go to the main core of the algorithm. We will explain how this expectation propagation algorithm works. Then we move to explain how this can be applied to a digital communication system. And then we will bring here two main applications, one to MIMO and one to equalization. So let's first focus on the system. I will try to, I skipped really many details to keep things simple as possible. And what I just faced to be really easy to explain is a linear system. So our problem here is just to solve a linear system. But U, that is here the unknown, this U is discrete. Okay, so they are discrete random variables, they are the unknowns, and we have this y, that it is the observation vector. So we have some mixture matrix that we would assume known, and then we have some noise. So this is a really simple linear mixture system that is the core of many digital communication systems. So many digital communication systems can be explained with this model. So let's face it, okay? To simplify everything, we assume that the dimensions are all the same. So the noise, the unknowns, and the observation are all n vectors, L by 1 vectors. And the matrix H will be just an n by n matrix. So the system is really simple. Okay. In the sequel, we will also assume that the samples in the noise are independent. So the covariance matrix is just identity matrix. And we are really interested in computing the posteriors. Okay, that's the goal here. We want to know the probability of every U, every entry K of U, once we know the observation. So this is our goal. The problem is that, well, we could try to solve this. Right? So if we are to compute the posteriors and get the maximum probability, if we want to estimate the value for UK, we could estimate every probability P of U given Y and retain the maximum value. Okay? The problem here is that being U discrete makes us to check for every possible combination. So the key point here is that being U discrete makes us to check for every possible combination in the system to get the one that provides the maximum posteriori probability. And that's maybe really impossible when dimensions are large. When we have a digital communication system with a very large constellation, and we have a system with large dimensions, for example, a MIMO system with many antennas, we cannot do this anymore because it's unaffordable. So what can we do? There are many approximations, but in the end, when the dimensions are really large, they fail. So we are proposing here a method that can be applied when dimensions are really large, and it's really giving a good performance. To end with the motivation section, we bring here a pair of curves from a paper of our colleagues in Universidad Carlos III, where they show that with this expectation propagation method, the EPD, their method, they can really move closer to the capacity limit. So here we have the curves for the mutual information of the channel for many approaches, and they show that with EPD we really outperform the state of the art. So let's see how this works. How can we get this? So the expectation propagation, perhaps the easier way to explain it is to start from the LMMSE. So if we really know how the linear MMSE algorithm works, it is really easy or it's easier to understand how the expectation propagation performs. So let's go over it. The model we have, if we want to compute the exact expressions for the posteriors, that's our goal in principle, what we would do is just to multiply what we know, that is this term, that is the likelihood. Here we get into the formula everything we know, the matrix H and the variance of the noise, and then multiply it by the priors. And then what we get is these probabilities of the unknowns. These probabilities are discrete. If we have a QM constellation, they are uniform discrete PDFs, in this case mass functions. So we could get those values in, but again, to compute the maximum values for these posteriors, we have to check all combinations. So the linear MMSE is really a good approximation. It works really well when dimensions grow to very large numbers. And what it does is just to replace these values here by some Gaussians. They say, okay, these are not discrete anymore. Just replace them by some Gaussian approximations. These Gaussian approximations are just some complex Gaussians of UK with some mean values and some variance values. So when we apply the LMMSE from the books, what we do usually in digital communications is just to assume that the mean is 0, because the constellation of the transmission is zero mean. And also, we take as variance the energy of the transmitted symbol. And that's what we usually do in LMMSE. And then we multiply these two PDFs to get the approximation QU to the posterior. And then we can compute this mu and c. And here is where the computational complexity is, because to compute this mu and c from these values, we have to invert a matrix of dimension n. So the complexity is n to 3. Okay? So this is what the LMMSE does. And now, how does the expectation propagation work? What it does is in a structure exactly the same that the LMMSE. It does the same. It has the same structure. So we copy it here. But the point is that the mean and the variance are no longer 0 and the energy of the system. So the expectation propagation, what it's doing is just trying to compute the mean values for every unknown and the variance for every unknown, for the approximation to the priors of the unknowns. That makes the whole product better approximate the true posterior. So in the expectation propagation, the goal here is to compute values for the mean and the variance of this approximation to the priors. Okay? And the expectation propagation does it in an iteratively way, so through S iterations. So here I bring the equation of the LMMSE. We can, once we know the values for the mean and the variance, we can compute the mean and the variance of the covariance of the approximation with these expressions. Or equivalently, if we want the particular entries of mu or the diagonal of C, we can use this expression, but there have been taken from any book. Okay. So let's see how the expectation propagation compute these values. So far we have just the same structure that the LMMSE. We want to compute some some mean and variance for the approximation of the priors here. That's really improve the wall approximation. See, now we are seeing how to do it. The starting point is the expression. So what we first do is to initialize the values to the mean and variance of the standard LMMSE, that is to 0 mean and to a variance equal to the energy of the system. That's the first we do. And then iterate. In every iteration, what we first do is just to include these values in the expression and compute mu and c, as the LMMSE would do. And in doing this, we really have the computational complexity of the LMMSE that is n to 3. It's cubic with a dimension. Then we marginalize this to get the posterior for every k, for every entry for every unknown, and we have it here. Okay. And next, we have the 2-3 steps that are the key point of the expectation propagation. It first divide the computed marginal. We already have approximated the posterior. We have it here, the posterior for an unknown key. And what we do first is just to divide by the already prior we approximated. Okay, that's the first step. We normalize, divide by this value. And we get what is called in digital communication the extrinsic probability. And next, what we do is just to get this result, multiply by the true one. So you have to pay attention to this step, because what we are doing here is just to divide by the approximation and multiply by the true prior here. This PU key is the true prior. If we don't know anything about the the unknown, we can approximate it by a discrete uniform probability mass function of the constellation. Okay? So we would put here the true discrete probability. And next, what we do is what is called the moment matching step. And here, what we force is that the whole term to the left to have the same moments than the term to the right. And the term to the right is this one, the already approximation divided by the approximation of the prior so far, multiplied by the true one. So we force these two terms to have the same moments. We do this for every k, for every unknown, iteratively through S iterations. Okay? To improve the convergence, we usually use forgetting factor, forgetting low. So we are not really using these new values here, but we update the value with this one and the previous obtained ones in the previous iteration. So this is the really core of the expectation propagation, where what we are doing is replacing the, for every k, for every unknown, replacing the already approximated prior by the true one and force that the whole moments match. Okay. So in the end, we just restart the iteration for the next one through S iterations overall. Here are a couple of details. When we do this moment matching, sometimes the moments of this product gets really low. And to improve the convergence of the approach, we keep it to a minimum value. And also we have to tune another parameter. We have this epsilon, that is the minimum allowed value for the variance of this product. And then we have this beta parameter that is the parameter of the forgetting low here. Okay? So we have that pair of parameters. So overall, and that's important, what we have is just that we have iterated through S time the LMMSE approach. So the complexity is S plus 1 times the complexity of the linear MMSE. Okay? To sum up and to end this section, and I understand that the question may be a little bit tricky, but it would be interesting that you retain the following. We have taken the structure of the LMMSE, where we have some means and variance to tune, and we have tuning using some approach, the expectation propagation, that really better approximate the full posteriors. Okay, that's the main idea here. Also, an important key point here is that the structure is that of the linear MMSE, but it is not linear. Why? Because when we have computed the variance and the mean in this structure, we use the observation. Okay? So it has the same structure as the linear MMSE, but it is not linear. Okay? That's why it improves the solution. How to apply this to digital communication systems? Okay. Here we bring the atypical chain model of the system, where what we have is the channel encoder, the modulation, the channel, noise, and the detector. The detector should provide these posteriors, so the channel decoder could really improve the output with this information. So modern channel decoders really use posterior probabilities. LLDPC, convolutional codes, they really take advantage of the probabilities rather than on hard decisions. Okay? So in principle, we would use this scheme. The priors would be that of the constellation, a discrete uniform one. And what we would do then is just to try to apply the expectation propagation to this system. However, in many systems, it is also used what is called a turbo detector. In a turbo detector, once we have end with this chain, we go back to the detector with the output of the channel decoder. Why? Because the channel decoder already provides us with a better estimation of the priors, okay, of the priors of the unknowns. So we can feed back these probabilities to the detector and then start anew with iterations of the expectation propagation. So how can we write this down in an algorithm? Okay, we have this structure where we have two loops. We have an inner loop here with S iterations and an outer loop here with T iterations. So this one is the algorithm I already explained to you in the previous section. It's just as it is. But we need to change just that, since we have a better estimation of the priors, in the moment matching step, we will use them. That's a first change of the algorithm. So we take the algorithm as it is, and then we place in this moment matching step the P by the PD that are the probabilities that the channel decoder is giving to us. And then we have to also initialize the inner loop with the output of the outer loop. And we do this by again using the expectation propagation. Okay? So these are the two main steps that we should modify in the algorithm. So the algorithm here is just the one I already showed you before with two main changes. Here, in the initialization, we no longer use the same values that the LMMSE, but the values that came from the channel decoder. And here, in the moment matching step, we don't use anymore the P, but the PD that are the outputs of the channel decoder. Okay? So those are the main steps. In this algorithm, if we do not iterate this, I mean, if the number of iteration of the expectation propagation S is 0, we don't have, what we have is really the LMMSE solution. Okay? So far we have this algorithm that can be applied to any digital communication system. The parameters that we need to define are these ones here, the epsilon, the beta, that I already discussed on them, the number of iteration of the inner, of the expectation propagation, and then the number of the turbo iterations. So as in every turbo iteration, we are just iterating the EP, the computational complexity, again, is sometimes that of the LMMSE. How can we apply this to digital communication system? Okay, let's see how this can be applied to a MIMO, for example. Here I brought many approaches in the state of the art of MIMO. Here I brought the exact solution, that is the map solution, that I already said that it's unaffordable when we have large numbers, that large dimensions. In this case, a large number of antenna. Okay? Then, since we cannot apply them, we resort to some approximations. And the approximations here that I brought in the state of the art are phase decoding, it's well known, or just sampling the PDF to approximate it. The LMMSE is a good one. The GTA or the CHEM, that are really two results that have been proposed in the last 5-10 years. All of them, except these two, the GTA and the LMMSE, are really unaffordable when the dimensions are large. Okay? So we have we have the LMMSE and the GTA. And recently, in the last 10 years or 8 years, some solution based on the expectation propagation have been proposed. I bring here also a curve from from the application of one of them, of one expectation propagation approaches, to show you how the GTA that is already, it was already a good approach, is really improved, outperformed by this expectation propagation approach. So the question is, okay, can we go further than these approaches with this method I already told you about? Okay. For MIMO, the system is exactly the same we have in the model. It's exactly the same. The only, perhaps the only point to remark is that now N is the number of antennas. So we have N transmitting antennas and N receiving antennas. We have the observation, and what we really want is to estimate the transmitted symbols U. So here the unknowns are the transmitted symbols. And we have, our goal here is just to estimate this posterior. We can get the solution as it is. So here there's nothing new. I just took the algorithm that I showed you before and put it here. I also bring here the equations of the LMMSE, but they are in the books. So we take this algorithm, define the parameters. The LMMSE has no parameter. The method by Sense and co-authors, the MPAP, just iterates the EP once and has no control on the convergence. The EPD has a control on the convergence, but it really has a large number of iterations. And now in our approach here, we just iterate 3 times. I mean, we have 3 times the computational complexity of the LMMSE and propose these values to improve the convergence. And what we get is really a good result here, where we see first that the LMMSE is doing a great job, even though we have large dimensions. We have a 6 by 6 and a 32 by 32 MIMO system with 128 MQM constellation. So this system is quite large. The LMMSE is performing very well. The previous EPD expectation propagation approach is doing well too, but it has some instabilities here, and it can be really improved. The approach by Sense has some instabilities over here. It's a good approach, but it can be, with the method we already discussed here, can be improved in even 6 dBs. Okay. This is given for 5 turbo iterations, and LDPC codes of half rates have been used. Okay. This has been already published. And let's move to the other application, that is equalization. Okay. In equalization, the problem is that, again, when the dimensions of the system gets really high, most of the approximations in the literature doesn't work. They don't work, okay? And here I bring a simple example where we simulated all this bunch of approaches for a polar constellation, for a polar modulation, a BPSK, okay? But if we moved from a bipolar to a 4-level constellation, all these approaches, most of these approaches just they don't work, okay? And we get the LMMSE, the expectation propagation proposed by us, and that is the optimal solution, okay? So there is room for improvement. How can we apply this to equalization? In equalization, we bring the model that we already explained in the digital communication section. And in principle, we can apply in a straightforward way because the channel can be included in a mixing matrix, but that it has some structure. In this case, it is top-leaf. So here, these values are just the tap of the channel. And then we can build this matrix and apply, again, the EP approach that I already explained as it is. And what we have is this block solution, called block solution, that it's really, it's really get an improvement compared with other methods, and in the case with the LMMSE. However, somehow it's a brute force approach, because we have to invert a very large matrix that it has the dimension of the word, of the transmitted word. So we have a complexity that is quadratic with the length of the whole word. So this is not really well, a good approach if the words are large. What could we do? We are working with LMMSE. So if we are doing filtering with this idea of LMMSE, we can think about the Wiener filter. Can we improve the Wiener filter with EP? Yes. We can build a Wiener filter that can be rewritten in terms of the expectation propagation to get a better approach. And that's what we did here, okay? Since in the Wiener filter, we just retain part of the observation, we are not taking into account the whole observation, the whole word, but part of it in a window, we get worse results. But once we iterate from 2 to 5 times the turbo, we get a really good result near, quite near to the block optimal solution. Okay? And the computational complexity of this approach is cubic with the window, the length of the observation. Okay? That's in the Wiener filter. And to end with this application, what we would again do is, okay, when we do this filtering, when we have a channel and we want to estimate the transmitted symbols, what we do when we use Gaussian approximations is to resort to a Kalman filter. Okay? So can we again apply the expectation propagation to improve the Kalman filter approximation for discrete unknowns? Yes, we can. So it's you have to do the maths, but you can build a forward step, the backward steps, then join them to get a solution and improve it with the expectation propagation. And the good news here is that in that case, the computational complexity is just cubic in the number of variables involved in the state of the Kalman smoothing filter. Okay? So if you do the math, what you get is really the same solution that the block solution here, but with a complexity that is linear in the number of symbols and cubic in the length of the channel. Okay? So this proves that the expectation propagation can be applied in a wide set of systems, and also that everything we know about the linear minimization of the mean square error can be improved when we use it to estimate discrete unknowns. Okay, and those are my conclusions. Okay, that we really brought here an approach that is quite simple in computational complexity, because it just has the complexity of the LMMSE 4 times the complexity of the LMMSE, and that everything we know about minimum square error apply to a filtering, to a Kalman filtering, to a MIMO, can be rewritten to better optimize, to better improve, or to improve the estimation of the posteriors. And this really had an impact on the performance of the detection. Okay? And that's all. Thank you for your attention, and if you have any questions.
So thank you, Professor, for the great presentation. And if you have any questions.
Can you give us some comments on the application to massive MIMO systems?
Well, in this case, the In this case, what we have is a 32 by 32. Perhaps this is not really massive MIMO, but you can imagine the evolution from 6 to 32 and from 32 perhaps to 100. Okay, and what we have here is just that these approaches compared to the LMMSE are really improving the solution by almost 10 dBs. And the computational complexity is exactly 4 times the computational complexity of the LMMSE. Still, is cubic with the size of the matrix. So if you have a 100 by 100 system, it's cubic with that dimension.
So how much time are we talking about? How much time are we talking about when you say, for this example, for instance, for the algorithm?
I don't know what you mean by time.
In second?
I don't know. I mean, you have to implement that.
Okay.
My reference is the LMMSE.
All right.
So if you
With
are
respect to that.
Yeah,
Okay.
if you are implementing the LMMSE, you just multiply that by 4.
Okay.
So the problem here is that if you are doing a zero forcing or doing an LMMSE, you have to invert the matrix. And that will take you a cubic computational complexity with the dimension of the antenna, and the number of antennas. And we are just multiplying that by 4 and improving this in 10 dBs. Because the step is really easy. I mean, it's just to better findings the mean and the variance of the LMMSE. You have a pair of parameters there that are the mean and the variance, and what we are doing just is to improve those values. You know that the optimal solution is highly nonlinear. When you try just in a case 2 by 2, you can see that the optimal solution is quite nonlinear. What we are doing here is somehow to get to the point where the observation is, and estimate for that point a good solution. Okay.
Any more questions? So I have one question: is there any plans for an adaptive version of the EP? For example, a solution like the recursive least squares for inversion of the matrix?
We haven't think about it, but in principle, if you have something that already works with an MMSE structure, you can think about translate that to the expectation propagation approach. So I mean, perhaps if we think about the LMS algorithm and we want to make that adaptive, perhaps there is a way to. We haven't investigated that yet.
Thank you. Any more questions? If that's the case, then let's thank once again Professor Fuentes.